Welcome to Quantum Photonics. Here we are with this very interesting paper and with a very interesting guest speaker. So, scaling up qubit counts in quantum computers is one of the core uh, needed in achieving quantum supremacy. One Alto research group is tackling this challenge with a new type of compact nanobolometer. Alto University researchers are the first in the world to measure qubits with ultra-sensitive thermal detectors, thus evading the Heisenberg uncertainty principle. To the chagrin of many physicists, the Heisenberg uncertainty principle determines that one cannot simultaneously know a signal's position and momentum or voltage and current with accuracy. So it goes with qubit measurements conducted with parametric voltage current amplifiers. But bolometric energy sensing is a fundamentally different kind of measurement, serving as a means of evading Heisenberg's infamous rule. Since a bolometer measures power or photon number, it is not bound to add quantum noise stemming from the Heisenberg uncertainty principle in the way that the parametric amplifiers are. Here we are with our special guest speaker. He will be speaking about the recent paper that his lab had published, and I'd like to introduce him to you. Professor Mikko Mitonen is a professor of quantum technology at Aalto University and VTT, working especially on superconducting quantum electric circuits and ultra-sensitive bolometers. He has published more than 150 scientific articles with more than 9,000 citations, including 4 articles on the top journals, Nature and Science. He has received 5 ERC grants in total, and Miko graduated with a doctorate in technology in 2005 from the Department of Applied Physics at Helsinki University of Technology. Although focusing on experimental quantum physics, Miko has also made major theoretical contributions. He is also the head of the Alto BSc program in Science and Technology and of the Quantum Technology major. Breakthroughs in research have enabled the commercialization of quantum computing devices, including the spin-out of IQM from Miko's Quantum Computing and Devices, or QCD, research group. He is one of the 4 co-founders of IQM Quantum Computers, and recently, Miko obtained the Nokia Recognition Award, the Vaisala Science Prize, and the Innovation Professor Award, and an honorary doctorate from Lappeenranta University of Technology. So he was also elected as a member of the Finnish Academy of Science and Letters and the Finnish Academy of Technology. So I'm very proud to introduce to you our guest speaker, to bring him on stage, and we are excited to listen to him, Dr. Mikko Mitonen. Mikko, welcome to Quantum Photonics.
Great, thanks. What a wonderful opening music, and thanks, Cecile, for the kind words. So I hope you're all now up to some science, and feel free to. I mean, let me try. I think Cecile told me that I have about a half an hour or something to go through the slides, and then we can have a discussion. But but so write down stuff, write down questions during my talk because I really want to discuss this topic with you later on. So I will not talk thoroughly everything, but I try to give you a little understanding of the topic so that you can ask questions. All right. So let's start the ride. I'm going to the next slide where I have my research group photo from last summer. I just wanted to show you some faces of the people who are behind this work. Especially there's a person that is encircled with a red circle, and that's Marzi, Martin Gunho, and he's my PhD student. He's been with the group uh, for almost 10 years now, I think. He started in the beginning of his university studies, came to my lab, and here he is still, soon finishing his PhD, and he's the man who made these experiments on the qubit readout that I'm going to talk about. All right, but of course, a lot of people have contributed, so I'm really thankful for the great collaborators and great people around us. We're really fortunate to have such a great group, and also Wei Liu from IQM has been contributing to this work a lot. So there's also this kind of collaboration going on. All right. Uh, then next slide, I just wanted to also point out some research leaders in our Center of Excellence, Quantum Technology Finland, that is led by Jukka Pekola, and Sabrina Maniscalco is the vice head of the center. And many of these people, especially Visa Westerinen from VTT and Mika Brunila from VTT, I have collaborated with them a lot on balameters, and that has been very important for the results. And of course, Pertti Hakonen, also his group, has was instrumental in getting our graphene balameter on the track and realized. So really nice to have such a high level collaborators on board. My research group, QCD in general, here is kind of a general picture of what we are doing in research. So we together with IQM, we invented the Unimon qubit. That's a new superconducting qubit that my aim is to make that kind of the let's say better in fidelity than the transmon qubits at the moment, and that would kind of allow for quantum computers to do longer calculations and error correction in the end. Um, but in addition to making qubits better, we need to find ways to scale up the numbers without compromising on that fidelity. Okay, and and in the university, I think we have to look into the future. And we don't look into the future only 1 quarter or 2 quarters, like the companies quite often do, but we look into the future, let's say 5, 10 years, and 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 we think what would be the bottleneck in 10 years time with the current knowledge if we don't do something. And and that's why we have been starting to develop this so-called millikelvin electronics. What millikelvin means, it means that you are at very low temperatures, close to absolute zero. Let's say in the temperature range of just 1/100th of a degree to absolute zero. So in that temperature, that's the same temperature where the qubits work, and I want to build these electronic devices that can be used to control, read out, and reset qubits at very close to the qubits, basically on a chip that is just then bonded together with the qubit chip. So um, and today I don't have time to talk about all of these topics, but I'm just talking now about the recent work where we combined now our bolometer development that we have been doing for more than 10 years now, well more than 10 years, um, with our qubit knowledge. And indeed, in this recent paper published in Nature Electronics, we were able to show that we can read out the state of the qubit in a single shot with this bolometer. And yeah, this was a very nice development, and also a surprise to us that we got it working so well. But before I'm going to that experiment, I just want to give you some basics of what do we call bolometry and what do we call calorimetry. Okay, so a calorimeter is this is kind of a concept picture of a calorimeter. So now I'm on slide 9. Uh, Sorry that I forgot to tell you when I'm changing the slides, but now I'm on slide 9. That is the first slide with the white background. Um, so here is a concept picture of a calorimeter. So this letter C inside the box means that there is some heat capacity in the system. So What heat capacity means that if you put in energy E to that system, the temperature rise of the system will be E over C. Okay, so let's say that a single photon is absorbed to your system. You have a temperature rise, and a calorimeter measures the temperature so quickly that it can detect these individual events. So on the right side, you have like a real-time trace of a temperature where the energy packet hits the system, temperature jumps up, and then there's an exponential decay because the temperature will then equilibrate with the bath. Okay, and and we were also very recently able to, I think, break some records in this kind of just a calorimetry of very low energy. So we were able to measure about half of zeptojoule energy um, energy resolution. I don't have time to go to the details of that, but I just wanted to say that actually these very sensitive calorimeters can also be used in qubit readout. You can see that if the qubit readout signal, if there is now more energy than half of zeptojoule, we can distinguish that energy from the background. Balorimetry means that you are not measuring individual energy uh, packets, but you're measuring average power. And if you have a very basically if you have a very sensitive and very fast bolometer, that can be used as a calorimeter. But just to tell you kind of the differences in the concepts. But I'm going to talk about bolometers later on instead of calorimeters because yeah, the bolometers, as I said, they are so sensitive and fast in our case, so we can use them as a calorimeters as well. Um, and yeah, there is some sort of highlight of our recent results. Well, or 2020, we were able to really break some records on bolometry and the extracted energy resolution as well. You can see that the energy resolution in that experiment that I'm going to talk about a little bit more in a second was only 30, a single 30 gigahertz photon energy, and that is a really fine energy resolution, and that is much better than what we actually need for high fidelity qubit readout, and but that is something that we can get. So I think the future looks very promising. But let's get to the chase. Here is a artistic image of our bolometer. So now I changed the slide from slide 10 one forward. Um, so there is an artistic image where you can see on the far right corner there is a photon coming in to this red zone, which is basically the red means that it's an absorber that absorbs the photon and that heats up, and the heat is then equilibrated in this golden wire along the wire, and the wire actually works as a thermometer in our case. I will explain soon why, but this is kind of the concept. And then if we go to the next slide, slide 13, you can see an actual microscope image of the actual device from the top. So this device is on a silicon chip, and it's a thin film metal. As you can see that the absorber is about 1 micrometer long. So it's a really tiny absorber. And we have to make it small, and we want to make it small because then it becomes more sensitive. You can understand if the energy is absorbed into a very small volume, it has a larger impact on the system than it would be absorbed into a giant volume. And we measure this bolometer by from the right side when we put some microwaves in there and we look at what happens to the microwaves when they get out. Basically, they will get a phase shift. So the oscillation in the microwave, the current and voltage oscillations will shift their phase. And that's kind of how we read it out. And you can see this is actually the reflection coefficient from the bolometer on the next slide, slide 14, where you can see that depending on the heating power to the bolometer, the resonance frequency is shifting. So this dip down is shifting, and that is exactly our signal that we are going to be looking at. then I go to next slide, which seems to be slide 17 on the numbers, where I just show you the results. Okay, so what I'm showing as the in the black symbols, they tell you the so-called noise equivalent power, NEP. So that tells us that how accurately we can differentiate different powers coming to the bolometer. And the units are here zeptowatts over root hertz. And you might not have heard zepto before, but yes, that kind of unit, it does exist. Um, 1 zeptowatt is 10 to minus 21 watts. So it's a very, 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 very tiny power. Um, so, but the lower the number is, the better, right? Because it means that if the bolometer in a half of second time, we can differentiate down to about 20 zeptowatts, which is the uh, like lowest numbers where the black markers go. And so we were pretty happy about this result back in the day we got it. And we could now use this NEP also to calculate that what if we used this as a calorimeter, what would be our energy resolution? And so it's not a measurement of the energy resolution, but it gives us quite well the value, and that turned out to be about zero point 0.3 zeptojoules. So quite close to the half of the zeptojoule that I told you that we actually then got in real time measurements for the energy resolution. However, here the time constant is a bit longish. You can see those are the red markers. So they are about it's about 100 microsecond or some tens of microseconds, and though that time constant is a bit long if you think about qubit readout. However, we were thinking that how we could improve on this metallic bolometer that I talked to you about. So we went to graphene. So now I went to slide 22 and then to the next slide, which is 23. There is an image of a graphene bolometer where the idea is that we take the metal into a single layer of graphene. So we shrink the volume a lot. Of course, graphene is in a way zero volume system. It's a two-dimensional system, but it still has some heat capacity, but it's much smaller than the heat capacity of that tiny metal wire. So if we go to the next slide, you will see that how the graphene bolometer looks a little bit in practice, or well, you can see on the left just some electrodes on top of it. It's hard to see the graphene on a microscope image like this, but on the right side, you see that similarly in this graphene bolometer, we do get this dip in the reflection, microwave reflection, so we can measure quite nicely with the similar techniques that we could measure the other bolometer. So then I go to the next slide, where I have the key results. So you can see that in the graphene bolometer, the NEP, that is, let's look at the graph on the top middle column. And there you can see that we can go down to 30 zeptowatts per root hertz in the NEP, but the time constant is only hundreds of nanoseconds. So now this result was very interesting for qubit readout, where you want to be on this 100 nanosecond time scale. And also the energy resolution that is on the middle bottom panel, the extracted one seems to be only H bar times 30 gigahertz. So very, very fine energy resolution. So this got us excited about using this bolometer in the qubit readout. And next, in the next slide, where the title says dispersive qubit readout, you will see that the idea is really to put in the readout signal that we send to the qubit directly to this absorber of a bolometer instead of this other chain which is on the top, where you have these isolators and amplifiers and stuff like that. So we are really measuring here the photon number. We are not measuring we don't get any information on the phase, and like Cecile told you in the beginning. That's why we can evade some noise sources. So on the next slide, you will see a comparison of the bolometer readout technique with the usual amplification technique. And you can see that we have much less power. We, we dissipate much less power in the bolometric readout case. It's much smaller in size. It's about the size of the qubit, whereas the amplifiers are much larger. So in our case, we wouldn't really have a major footprint problems. Um, and there's a natural frequency conversion in the sense that we don't amplify the signal, but it just gets absorbed, and we can read out the bolometer in a very different frequency range. So we can dedicate some frequency band out of the qubit band to the bolometric readout. And there's it's a cold bath. That's what you want, and there is no added quantum noise. So that is that. Those are the advantages. And if we go to the next slide, that is 47, you will see that we actually used this metallic bolometer in these experiments, not the graphene bolometer yet. So there is yet to another leap to be taken when we use a graphene bolometer for qubit readout. So in the next slide, I will just wanted to say that um, how the qubit readout works in this case. So depending on the state of the qubit, there are actually two resonances in this qubit readout circuit. The one on the with the red color, and the one with the blue color. And now we drive the system in resonance of that blue dip. So if the qubit is in a state 0, the ground state, then we start to resonate the readout circuitry. And so it means that we have our signal will be in the amplitude, in the power of the tone that is going then to the bolometer from the readout circuit. So on the next slide, you will see slide 49, you will see just a chip. So we have a qubit chip. There is 6 qubits on the same chip, but we only measure one of them with the bolometer. And on the next slide, you will see so-called Rabi oscillations on the right, which means that when we are driving the cube, and these are measured with the bolometer now, by the way. This was the first time I saw Rabi oscillations measured with the bolometer, and it's so beautiful that that then we went for the single shot experiment as well. This was really motivating us a lot because there's only 500 averages here. It's an averaged experiment, but not average much. And the Rabi oscillation basically means the signal is going up and down there when you go to longer and longer qubit excitation pulses. It means that the qubit is rotating between zero and the states 0 and 1. And if we stop the Rabi oscillations, for example, to the one of the yellow pixels, it means that the qubit will then be rotated from 0 to 1. So this is a standard way to measure the qubit, except that now we did it with the bolometer, not with the amplifiers. All right, and then on the next slide, you will see that we started to, or let's take two slides. So now I'm on the slide 59. So here you can see um, on the in the center, you can see our single shot distributions. So we sent in these measurement pulses to the qubit, and the blue one means that the qubit was in a ground state when we sent in the measurement pulse, and the red color means that it was in the excited state. And we get very different distributions depending on the qubit state. And if we put a threshold where the dashed line is for the signal, so then we get about 60% readout fidelity, which means that um, about 20% of the time we make a mistake in the readout. So the fidelity is not super high, but it's much better than guessing. It's much better than guessing, and you can clearly see that that yeah, even with a single readout pulse, uh, we can read with the bolometer the qubit state in a single shot. So basically, if we send in a single pulse, readout pulse, and the detector signal, the bolometer signal, falls to the left of the threshold, then we would say that, oh, now the qubit was in the ground state. If it goes to the right of the threshold, so to higher voltages, then we say that the qubit was in the excited state. And it turns out that our readout pulse is actually quite long because the bolometer is a bit slow, this metallic one. And that is the reason for the infidelity. So if we take out the fact, the errors that happen because the qubit gets decays during the readout pulse, then the fidelity already would be more than 90%. And now we have a really great path towards 99.9% readout fidelity because the we can change the bolometer to the graphene bolometer, and we can make further optimization to the circuit so that we can reach that goal. And I think that would be awesome. So thanks for your attention, and I hope there is quite a bit of questions and discussion now.
Yeah, thank you so much, Miko. And we are now announcing to the audience that we're opening the floor for questions. If you have questions, please raise your hand and we will bring you on the stage. And just to reset the room, we're now talking about the paper that the laboratory of Miko had recently published, and it's about a new method of measuring qubits which promises ease of scalability in a microscopic package. So, yeah, Bob, can you hear me? For those who came in late, I would just like to reintroduce our guest speaker. There were several people who came in late, and probably I think they have questions. So, uh, Dr. Professor Miko Mutinen is a professor of quantum technology at Aalto University and VTT, working specially on superconducting quantum electric circuits and ultra-sensitive bolometers. He has published more than 150 scientific articles with more than 9,000 citations, including 4 articles in top journals like Nature and Science. He has received 5 ERC grants in total, and Miko graduated with a doctorate in technology in 2005 from the Department of Applied Physics at the Helsinki University of Technology. Although focusing on experimental quantum physics, Miko has also made major theoretical contributions. He is also the head of the Alta Bachelor of Science program in Science and Technology and the Quantum Technology major. Breakthroughs in research have enabled the commercialization of quantum computing devices, including the spin out IQM from Miko's Quantum Computing and Devices QCD research group. He is one of the 4 co-founders of IQM Quantum Computers, and recently Miko obtained the Nokia Recognition Award, the Vaisala Science Prize, the Innovation Professor Award, and an honorary doctorate from La Peranta University of Technology. He was also elected as a member of the Finnish Academy of Science and Letters and the Finnish Academy of Technology. So yeah, that's our speaker, Miko. So we have Mustafa who came here on stage. I think he asked a question earlier here on the room chat, and I think Dash is also raising his hand to ask some question. I hope Dash is on stage right now. Yeah, and he has no problem in coming up on stage. So yeah, I gave him. Okay, Dash is here. So I would just like to, initially, Miko, I would just like to ask you about the spin out IQM first. Is this the establishment of a separate group or a laboratory, or do you have this a group, the IQM? Are you also trying to do some kind of startup, or will that laboratory um, also have more specialty?
Yeah, okay, I can say a few words. Um, so we started. I mean, IQM Quantum Computers is currently a limited liability company that has raised more than 200 million euros of funding, and it has more than 250 people. working in there. IQM is completely independent of Aalto University, so it's its own company, and I'm one of the co-founders. The two there was two co-founders who worked in my research group when we founded the company, and then one co-founder that I actually did my PhD with him in the same lab. So there's a tight connection between the QCD research group and all the co-founders actually of IQM. So yeah, I mean, we span that out about 5 years ago, and the company has done very well since. Currently, I don't work for IQM, but of course, I'm happy to always tell about the founding story and such.
Yeah, thank you. So, yeah, I was curious because I thought that it's really a spin off. And I had posted your article from Alto, not from the other, in my Facebook account. And there was some interest in, with Dorita Hanorov about your article here. So she was asking you about maybe a startup that she heard before. So maybe this is IQM. And thank you for clarifying this because I thought that there was something big coming in the introduction that you have here for your bio. So yeah, I would like to give the mic to people who came in on stage. Of course, I have a question and later on, but. I would like to give the priority to those who came on stage. And so, yeah, welcome Mustafa Dash and also Vincent who came in here. So, yeah, if you have other people have questions, just feel free to raise your hand. So, um, Mustafa, I'd like to give you the mic now.
Thank you, Cecile. Thank you, Dr. Miko, for a great presentation. Um, I guess it's exhilarating to work on avant-garde subjects like this. Actually, I have two questions. First, what are the main technical and material challenges you have faced while integrating graphene bolometers into Qubits readout system? And how have you overcome these challenges?
All right. Um, the graphene bolometers, as such, turned out to be challenging to make. Um, I'm pretty sure that once I mean, now we have basically we got one of these graphene bolometers working, made by really like a, let's say, handicraft, really like making single devices, taking graphene flakes from basically carbon, um, and taking those individual flakes, picking them up, putting them to the right position on the chip, putting on leads, and that was very time consuming. But we got so this one PhD student from Pertti Hakonen's group, he got one of these working together with us back in the day. I think that was about 5-ish years ago, and and that's how we got the 2020 Nature paper uh, on it. However, then we started to think that we need to do these graphene bolometers in a more scalable way, because if you do them one by one and it takes days, it's just not gonna be industrially relevant, right? So then we started working together with VTT, so Mika Brunnila and others, and to make a scalable process to produce these graphene bolometers. And it really took us many years to get that process developed. Fortunately, now it seems to work. So we put recently a paper on archive on these Josephson junctions that are gate tunable and made with this process. And as we speak, we are kind of doing these bolometers so that we could then use them for qubit readout. So maybe it may be that the qubit readout is even the very first application that we will try these graphene bolometers. But yeah, the graphene itself is, so you asked about the material challenges in graphene bolometers. Yes, to make the good contact, clean contact between graphene and the metal, the superconducting metal, we basically use aluminum. That has to be done very carefully, and you have to know how to do it. If you don't know, it will be dirty, it will not stick, it will not work.
Thank you, Doctor. The second question is like the first in the same object. Um, how do the improvements brought by using graphene bolometers for single shot readouts affect the scalability of quantum computers? Is there a direct impact on the viability of large-scale quantum networks?
Yeah, what we want to show that we can achieve 99.9% readout fidelity in, let's say, 50 nanoseconds time only. And if we can show that, I think people will get convinced that this is the way to go. And we also have shown multiplexing of these bolometers. So this is something also that if you want to build a quantum computer, you don't want to have individual lines going to every bolometer. But we've shown that you can read out and excite several bolometers with just a single line by tuning the frequency. So I think once we've shown that, and we've shown that it's also kind of a durable uh, system, yeah, I think then it can be a no-brainer to just to try to start to integrating it.
I wrote one question, simple question in the chat uh, about your test. Did you make the test on one qubit or a set of qubits?
Yeah, like I showed you the chip that there were 6 qubits on the same chip, but we just choose one of them and we were just measuring one of them. But we could have measured another one as well. Um, yeah, we did it now on 1 qubit, and but it but we also did, like I said, we also did show that we can read out several bolometers with a single line, like in a frequency multiplexed way. So it's not very far. It's not very far from actually measuring several qubits, but we want to put our focus our efforts now in the improving the fidelity, because we think the multiplexing is, there is nothing fundamental there that can go wrong. It's just you just need good engineering.
Thank you very much and good luck for the next research. Thank you.
Thanks.
Yeah, thank you, Mustafa. And now we pass the mic to Dash.
Good morning. So I was definitely one of the people who came in late. So I'm gonna ask some some very basic questions because I'm also not that well read on quantum computing, um, doctor. So my first question is actually to kind of make sure I'm aligned. Heisenberg's uncertainty principle. That's like the thing where we we can't track the location and the movement a particle at the same time. Is that accurate?
Yep.
Okay. So as far as like quantum computers, I see things that I'm recognizing certain terms like qubits, which is like the um, the quantum version of the bit of the classical computers. So these are the basic units of information. Um, my my question with that is, first, are these quantum computers are they here to help us better accurately understand and measure things that are happening in the quantum realm? Is that their like sole purpose?
Well, no, no. The the purpose or the reason why people are and we and others are so excited about quantum computers and we want to build them and make them useful is that quantum computers are mostly or most interested being used in solving mathematical problems, computational problems, and there are some algorithms that we know that can be then run natively only on quantum computers, and quantum computers would give you speed up. It would give you speed up in for example, problems related to cryptography, in problems related to modeling chemical compounds, so basically drug design to some extent. They would speed up also some simulations of, for example, I don't know, weather, for example, weather simulations or some other simulations that are then used to provide us services. So quantum computers are new type of computational devices that solve problems in a very different way than normal computers. And when you know the way how to use that different way to in your advantage, then you can basically solve problems that are now unsolvable.
Okay, got you. So it's like bringing more efficiency to the technologies and both like mathematical models and tools, as well as the technologies and computers that we have um, today. So it's bringing more efficiency. Essentially, that's what it's here for.
Yeah, it's gonna make many things more efficient, but also it will create new applications because it's a fundamentally different disruptive technology. So it's gonna create new applications like, for example, electricity created, of course, computers in the end, and cell phones have WhatsApp. It has created own applications, this technology, because it's so fundamental, so fundamental step to new technologies. It will also create new applications. We don't know yet what those new applications will be because they're just unimaginable at the moment, but I'm sure there will be.
Got you. Okay, I think that completes my questions. I'll pass it over to Vincent. And thank you, Cecile and Bob, again.
Yeah. All right. Let's give the mic to Vincent.
Hello. Um, how fantastic. This is incredible. Um, thank you so much for coming to Quantum Photonics, first off. We sure really appreciate you. Uh, I have so many questions, but I'm going to limit it so I don't take up too much of the floor so I can yield it to others who have questions. Um, Scaling factors, or moreover, is there anything? Hmm, I'm going to leave my contact information in the LinkedIn for LinkedIn. Please get a hold of me if you like. I'd really like to help you out. This is stuff that can really change the world, and I would really like to just see it come to fruition.
Thank you, Vincent. So we also have Kevin who came up on stage. Yeah, welcome, Kevin. Yeah, I'll give you the floor if you have questions to ask.
Oh yeah, hi. Yeah, this is yeah. Speaking of that theoretical theme you're talking about, this is. I just woke up on a Saturday. It's great to wake up to, so I'm kind of in a dreamy state. So maybe I'll say something theoretical right now. With when you do both the qubit resonator and bolometer chips are mounted on their individual sample holders, which are placed in separate magnetic shields and attached to the mixing chamber in a plate of a dilution refrigerator with I think a base temperature of 12 MKs. But when you do that, if you couple that with forgive me for something that I keep bringing up, ultramagnetism. Uh, so on the theoretical state, if the newly discovered form of magnetism, ultramagnetism. So if you add that to the mix, do you think it's a weird mix of properties from the other types of magnetism? The electrons in ultramagnets spin in alternating directions, like in ferromagnets. Anti-ferromagnets resulting in no net magnetization. So I'll throw that. Maybe later I'll have something more, more down to earth to say if I can come up with something. If you have anything to say about that.
Well, so we have the magnetic shields because we want to protect the systems from spurious magnetic fields. Of course, also we have a little coil that we then use to control the magnetic field that the qubit experiences. We can change the qubit frequency with a magnetic field because there's a little superconducting loop in the qubit. And when we change the magnetic field that is penetrating the loop, so magnetic flux, then the properties of the qubit change. Now, there might be, of course, some applications on like antiferromagnets or some other sort of even more peculiar magnetic states of matter in quantum computers in general. I'm just hard to say exactly what those would be, but certainly it's something that people might want to look at. Myself, I'm not really kind of that kind of a materials researcher. We are more device researchers. So if somebody comes up with a good material, we'll build devices out of it.
Oh, okay. Yeah, thanks a lot. I'll try to think of something more, you know, more to do with your specific research to say while I'm waking up. So, thanks.
Thanks.
Thank you, Kevin. Uh, Miko, you were about to speak.
Yeah, I just said thanks also.
Yeah, all right. Thank you again. So you mentioned the potential for achieving higher fidelity single shot readout through improvements in chip design and experimental setup. Could you elaborate on what specific improvements are being considered and how they might impact readout fidelity?
Yeah, so now we lose more than half of the signal because the way we channel the readout tone to the qubit readout resonator and to the bolometer eventually. So putting a little capacitor to the line would actually give us more signal. Also, we lose some of that signal in the components like a microwave switch that we have between the qubit sample holder and the bolometer sample holder. So by just taking off those extra components, we also get a little bit more signal. Those are, let's say, still relatively minor advantages. What we think that can give us even greater advantage is that we will change the metallic bolometer to the graphene bolometer I already mentioned, and then increasing the frequency of the qubit readout resonator. So increasing the frequency has two effects or several effects, but two effects that I'm going to mention here. One is that you can run the resonator with more photons because the frequency is further off from the qubit frequency. So um, so then you can have more power. When you have more photons, there's more power. And if the frequency is higher, the same number of photons will give you more power because there's more energy per photon. The photon energy is the Planck's constant times frequency. So these are kind of the improvements we are making at the moment.
Yeah, thank you. So, what are the potential implications of achieving a single shot readout with nanobolometers for the development of fault tolerant quantum computing architectures?
Yeah, for fault tolerance, that's why I mentioned this 3 nines of fidelity and 50 nanoseconds of time, because in fault tolerant quantum computing, you really need to be able to measure quickly and feed back that information to your system, preferably quickly. So if we can read out the system in 15 nanosecond time, and if our measurement device is now at millikelvin, the cable length is going to be short, much shorter than if you would have an amplifier, again, amplifying it to room temperature. So I'm imagining that far in the future, we have this millikelvin electronics placed very close to the qubit chip, and there will be very little time delays between the signals and very little return time for the signals so that we can really use them in fault-tolerant quantum computing efficiently.
Yeah, thank you. So, there was someone who sent me a question here, and but I'd like to ask because I saw Mustafa flashing his mic a while ago. If he had some questions or comment.
Yes, thank you, Cecile. Actually, I would like to take this opportunity to speak to a great specialist in quantum computer for a better understanding. Dr. Miko, among the different attempts to develop quantum computers, which one seems the most promising to you and why?
To me, superconducting qubits seem most promising, and I think it's just this technology has now shown it's basically 2 decades old idea to use superconductors, Josephson junctions to build qubits, and actually in the way that we are doing it now, actually, yeah. So, um, and during these 2 decades, the quality of these qubits has exponentially gone up, and it's still going up. It's amazing how it can develop year after year exponentially. And also the number of qubits you can put on a single chip and control uh, simultaneously, even if you like, that has also gone up exponentially. So this technology has shown that it's getting better and better, larger and larger scale. And to me, there doesn't seem to be major roadblocks of doing this to the end, basically, or it never ends, of course, but to the point where quantum computers can become useful. I mean, we are very close. If you think that 20 years ago it started.
And in your opinion, what will be the first practical application of computers, and how soon might we see them emerge?
That's a good question because there is kind of two possibilities here. Um, I'm convinced that in about 15 years' time, uh, quantum computers have become fault tolerant in a sense that you can do very long calculations with them. Um, and and that's the time where the known algorithms that are known now can yield business advantage to businesses. So that and when that happens, of course, the developers of quantum computers will get a lot of funds from the profits, and they can start to develop even better quantum computers and larger quantum computers. So that's a very positive scenario. Um, but for those who think it's too long time, I can tell that also it's my sort of gut feeling that quantum computers will bring a useful sort of practical advantage even faster. Of course, it's this is just a gut feeling. There is no mathematical proof about it. If there was, it would be amazing news. And I think now the most important thing, actually, in addition to improving the machines, the hardware, is to look for algorithms, look for ways to use these early quantum computers. Let's say that we'll be here 3 years from now in practical use cases, and that's basically yeah, it's a math problem, and now I think mathematicians, physicists, everybody should be cracking that math problem.
You told us about the past 2 decades about superconductor. How do you see the field of quantum research evolving over the next decade?
It's gonna expand. It's gonna ramp up even more, because the closer we get to practical quantum advantage, the the more there is going to be funds, the more there's going to be also people. What I'm seeing here now is that there's a huge number of young people who have now grown in this sort of quantum uh, era where quantum is real. We have we have real quantum computers, working in Finland, a lot of them, and in the world even more. And people are just excited. They just want to make these machines work even better and useful. And we have now like kids graduating from the high school, and then they want to jump to this field of technology, which is great.
Is there an international in research, or each country has his own research? And in the same way, what do you see as the main barriers to the widespread adoption of quantum technologies?
There is, of course, really a lot of international collaborations in the scientific domain and also in the industry. It's not that one company can do it all, or it's not reasonable that it's not sensible that one company does it all. So there is a big value chain and network of companies that operate in this field. Um, and the main, did you talk about the main hurdles or what we should? I think, yeah, like I said, I don't see very uh, big sort of technological showstoppers. Of course, there's a lot of things we need to develop, but I see solutions instead of problems. Or actually, the problems to me are kind of they are delicious because I want to crack them, right? I want to solve them. If there were no problems, I would be very desperate, and I would probably just get depressed. But now there are so many nice problems to solve, that's great. What I think is really important for the field in general is that people, in a way, understand that it will still take some time for quantum computers to become useful in practice, and we and kind of have the trust that it will work. So we have to keep on investing to this field. And I think now the mentality everywhere is that yes, we should invest, we should invest. I hope that it will stay this way, uh, uh, so that there is no sort of downturn of the mood, because we really need this. We need this quickly. It will solve so many problems.
Thank you very much. One last question. I promise, Cecile. What ethical and social impacts do you foresee with the development of quantum technology?
So that question was probably also for me. Yeah, I think it's very important to think about the ethics of quantum computing, and there are already regulations. I mean, regulations. It's kind of a little bit strange that the technology that doesn't yet have practical use case is already export controlled, for example. Um, um, but that's the way it is now, and I think it's extremely important to make use cases, or that the first use cases of quantum computers are not sort of ethically or morally questionable, that they clearly just improve the quality of life of people, and I think that's extremely important, because this is a technology that will increase the quality of life of all people on this planet, and we don't want to make people think that it's somehow dangerous.
So yeah, I would just
What
like.
make people, excuse me, what make people very afraid is the connection between AI, robotics, and quantum computers. This is what will make us afraid.
Well, okay, you're kind of thinking that there would be a super robot that is so much smarter than we are, and there's no use anymore for for humans on this planet. But I don't think that. Um, I mean, I don't think that it will be like that, or it will not be a disaster. I think we have to AI, especially now. I mean, AI is now developing, and it's already really useful, and it's developing also quickly, and we need to regulate it. We need to make sure that AI is not going to destroy some of the structures that we have built that are good for us. For example, I'm a bit worried that if we don't change the way internet works, it will be broken by AI pretty soon. Um, so we need to do that regulation anyways, and we need to, let's say, rebuild something to be stronger, to take the new environment where AI is operating into account. And when you add quantum to that, okay, AI can become smarter, become faster, but we have globally, we should have already the infrastructure in place to regulate it, and we should already have the regulations in place when that happens, so that I don't see that adding quantum to that will be somehow disaster. On the contrary, adding quantum to the good use cases of AI can be really beneficial.
I think the race for leadership is what prevents this regulation you mentioned, and we need these regulations. But this race prevents.
Yeah, yeah. It's in some sense I hear you, but on the other hand, um, it it's not necessarily so because at least in the EU, uh, EU is the best in the world in one thing, and that's regulation. So, um, and and in the EU, you know, you want it's understood that we need regulation exactly because we want to avoid the the problems that may arise. And even if there's a race, I mean, you don't want to compromise on that idea, because even the technology you are developing yourself could then make big problems. For example, let's say that the AI would be now 10, 100 times faster and cheaper, and it would just run wild in the internet, and it would send you 10,000 emails per day that would be so well written that you don't know whether it's from your wife or your partner or whether it's actually AI. I mean, that would basically make email useless. So much junk email that it's gonna be useless. So just forget it, forget about it. And to prevent that from happening, there is a solution to that. um, but you need to enforce the regulation that kind of forces people to take the solution into use before it's too late. And that's what I'm talking about. I mean, if you see problems, even if there is a race, you want to develop the technology, but you also want to protect yourself. You will lose if you don't protect yourself. Even if you would build the smartest AI on the world, if you don't protect yourself, you're gonna lose the race eventually, right? The other people will then go past you because you forgot to protect yourself.
Yes,
Yeah, thank you, Mustafa. So, yeah, I think I would just like to comment that, of course, we still have one of the big problems in quantum computing is that quantum error correction. And of course, there is still a lot of noise. That's why what's happening in every experiment or in any system to become very disruptive, is side developments and also the experiments and the discovery of the group of Miko here because it is very helpful in trying to help solve the quantum error correction for those who are doing it. So I think in any system, it looks like nothing is happening for a long, long time. That is what you call a percolation stage, and everybody's doing work or experiment along that field. And suddenly, like several years had passed, nothing was happening. People will say that there is like a quantum computing winter, or in the past they would say a neuroscience winter, and then suddenly it explodes. It reaches its tipping point, and that's something that we could not stop anymore, and it changes the world. So that is like my observation because even in AI, those AI researchers before the large language models came in, and yeah, I think 2 years ago there was really a lot of money being put in quantum computing research, and in fact, I think there was just like an equivalent of the a convention 2 years ago with the new people researching in quantum computing. So people were so excited about that, and then suddenly the LLMs, the generative AI, came in, and then it tried to take over the hyped limelight here. So, but I think, of course, people are trying to combine quantum computing and machine learning. And I think that is very, very helpful and has already used cases now because, for example, companies like Cambridge and also Honeywell has merged into together, and they made a third company which is doing now quantum machine learning for the finance industry, and they are selling that in as in a software as a service for the finance industry. So yeah, there are a lot of use cases, but maybe we just don't know that yet. And just like what Miko had said earlier, for example, electricity, when a technology first comes, we still don't know the use case, but eventually you are able to discover new use cases. So, and also in terms of ethics, a lot of people also in the field of science are saying that people were very apprehensive about like artificial intelligence. But I think 5 years ago there was a convention in Asilomar, and they were saying the biggest existential threat at that time was about biotechnology. And people should also pay attention to that because with the advent of AI, just like Eric Schmidt, the former chairman of Google, was saying just now, that there is going to be an explosion of biotech companies who are actually implementing new discoveries that are happening because of artificial intelligence and potentially quantum computing. So yeah, there are always many issues, but we have to try to balance that out. And I'm also very glad that the EU is trying to look at regulations on this in other areas. It's not yet being considered very seriously. So, but I'm sure they are. But the EU is always the first to do that. Yeah, that's just my comment. So, I would like to ask Miko, is there another step forward to scale up what you had discovered here on your paper?
Another step. I mean, well, I did talk about quite a lot in the next steps we're taking here in the qubit readout. Of course, then for control and reset, we have also major efforts. So um, yeah, I'm as I said, I'm trying to build these little systems to millikelvin that would do the control readout and reset for you right there, instead of having to take the signals back up to the room temperature and use normal logic to do that, because it's just gonna be too slow, in my opinion.
Yeah, thank you, Miko. So, yeah, I would just like to, this is just my personal opinion. I would just like to say that you must be a good mentor because you mentioned this student under your staff working on your lab who had stayed with you for already 10 years. And I see that, you have a lot of people working under you. And I think it is very important to be a good leader and a mentor because your students or staff would like to stay under your guidance and mentorship, and of course help the world discover more things. So I would like to just say that I really appreciate that. So any comments about mentorship and also the people working under you now? How many people are working in your lab?
Yeah, we have about maybe 15 people now in the lab, and during the summertime we get summer students, so then it can go up to 20.
Uh, I have a question. You're speaking of the of operating temperature. Um, have you addressed yet? Lowering the temperature, to reduce the thermal noise. I know that's technically challenging. Like improved design. Like reducing the size and geometry optimization and material doping is something I heard about. You know, by the bolometer material with specific impurities could manipulate its electrical properties and potentially reduce noise. And like I brought up the shielding, for ultramagnetism, but that's something different. And readout electronics, you know, uh, like low noise amplifiers to improve the data processing algorithms, stuff. Hopefully, I haven't brought too much of that more practical stuff up. Any thoughts on that?
Yeah, we do have an invention called quantum circuit refrigerator that is basically an active cooler of this electromagnetic degrees of freedom that the qubit sees, so that we can also cool to lower temperature than the fridge with that. At least theoretically, it works that way, and I think also in practice we have shown it. Um, so yeah, we have paid attention to that, and to be able to cool to low temperatures or even lower temperatures than now. But one of the problems actually there is it's not so much about the fridge temperature. The fridge goes to like 10, 20, 12 millikelvin, like we said here. I mean that's low enough temperature, but it's kind of trickier to get the all the components to that low temperature. And there are like different developments now to make lower temperature attenuators, for example, that they stay cold even if you run signals through them. Um, and yeah, we have some ideas how to also maybe how to bypass those problems that come from the finite temperature. I can't really tell you much about it now. I mean, it's something that we are cooking in the background. Yeah, definitely one should study quantum mechanics and quantum information theory, but then it's kind of quantum field is so large that there's just no one path, but there are several paths, and depends on what you want to do. Whether you want to be the person who fabricates the chips, or do you want to be the person who designs the chips, or do you want to be the person who is running the chips? Those require all different special skills. But certainly quantum mechanics, programming, mathematics is always useful.
Thank you.
All right, so maybe I have to Cecile start going back to my weekend routines here. Is that
Yeah.
okay?
Yeah, I was about to ask you a question because anyway, I was thrown out of the room a while ago. So it took me some time to come back, and I promised you that I will ask you that question after 1 hour and a half has passed. And if you would like to go back to live soon, that's okay because we got a very we heard a very great presentation from you, and you answered all kinds of questions. So we are really very appreciative that you came and tried to be our guest speaker this time, and we hope that we can invite you again because I'm sure that your lab has many very important papers, and we'd like to hear from you again. So yeah, at this point, I'd like to pass the mic to you if you have some last comments before we close the event.
Oh, thanks for listening and thanks for the questions. It was nice to have a chat.
Yeah, thank you. So I'd like to thank the people here on stage, Mustafa, Dash, and Kevin, and those who were here on stage earlier. And thank you for listening, and please check us out on the next rooms. And this is one of our very important rooms in quantum photonics. And of course, we will be rooting for the future studies of Miko in his lab and whatever spin offs that will be happening in the future. So thank you so much again, Miko. And Bob, maybe you would like to speak before we give the mic to Darcel to help us do the countdown to close the room.
I just wanted to thank you on behalf of everybody in the audience. This spectacular discussion tonight. Thank you so much.
Yeah, all right. So we'd like to give the mic to Darcel now to help us close the room.
Thank you, Doctor, for a great talk. Um, to close the room, we're going to start our countdown from lucky number 7. Is everybody ready?
Ready.
Ready?
Really?
7.
Seven.
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 Kevin,
Seven.
6.
Sixer.
Dash, 5.
5.
Mustafa, 4.
Quatre.
Bob, 3.
Three it is.
Cecile, 2 X.
Dos Equis.
Good doctor, you're number 1. Please call out our last number.
One.
Thank you. Thank you so much, Miko. And thank you, everyone. See you in the next rooms.